Hello, Honors Chemistry, and welcome to Introduction to Chapter 2. This is going to cover sections 2.1 through 2.5. A lot of this is review from your summer homework. So, as needed, refer back to your summer homework, either the lecture videos or the notes that you took, because that's what's going to be helpful here, right? So first of all, it opens with the concept of scientific notation, right? During the summer and back in middle school and I don't know where else, right? But you've learned about the concept of scientific notation, right? Where when we say something times 10 to the positive exponent, that means giant number, right? This means 5 places bigger, right? Which means that we are talking about a giant number versus when I say this, right? Negative means 5 places smaller, right? Which means a tiny number, right? This number is greater than 1 and this number is less than 1. That's super important because that's going to give us a quick way to double check our math, right? If we are talking about a number of atoms, for example, right? A number of atoms is never going to be a negative exponent. That doesn't make sense because you can't have less than an atom, right? So it ought to be somewhere in the land of positive exponents, right? Whereas if we're talking about, for example, the number of grams contained in a few atoms, right? The number of grams of a few atoms ought to be a negative exponent because we are talking about a mass so tiny that honestly we find it hard to wrap our mind around, right? And then that would make sense, right? Whereas a positive exponent would mean some ginormous mass, right? So here is where our understanding of scientific notation is really important, right? Not to mention it helps us enter things into our calculator correctly, right? And so it's just important, right? If you feel like you need a refresher on scientific notation, come see me and we can chat about it. All right, so significant figures, how to record measurements. So here we have a ruler, right? And the rule from your guys' book says we will always record one place beyond what is shown, right? So if we look at these arrows, right, this arrow is the same size, right? First, we would drag it down and see where it stops, right? And that's where it stops. Then we need to assess our ruler. What are we measuring in, right? Let's say we want to use centimeters, right? Then we would take a look at our ruler and see, so we've got ones, and then we've got each of these little lines, where each of these little lines represents a tenth, right? So we can be sure that this arrow is 5 and 6/10 because that's what's marked off on the ruler. Then beyond that, we have to use our estimation for one place beyond that, right? So I will look, and to me, it looks like it stops exactly on there, so I'm going to say 5.60, right? Alternatively, I could look at these two lines, visually cut that space in half, and see is it at the half, less than the half, greater than the half, and pick a number accordingly, right? Likewise, if I wanted to, I could use this as a millimeter measurement, right? Where in millimeters, this is marked off to the ones, right? As in this is 55, 56 millimeters, right? Marked off to the ones place, and I could estimate one place beyond that, right? Does that make sense? Both of these measurements say the same thing. Alternatively, it offers inches, right? Where here is where it stops, right? And then I can see, this is 2 point. And then we'd have to look here, 1, 2, 3, 4, 5, 6, 7, 8. So it's measured off in eighths. What even is that? This is why inches are ridiculous. Who thinks in eighths, right? Now, when we talk about the level of precision we can get from a tool, right, I hope it becomes crystal clear here, right, that between the centimeters and millimeters, we get better resolution of our measurement, right, as in the distance between the graduations is smaller in the centimeters and millimeters than it is in the inches, right, which partly has to do with the quality of this ruler, right, but anytime that's true, right, that we're going to get better resolution, right. All right, so here, same thing, right, we've got a graduated cylinder, and we would read the bottom of the meniscus, right? So we'd see that, this is in milliliters, so milliliters, and we would see that it's marked off into the 10, 11, 12, 13, 14, 15. So it's marked off to the ones place. So we would use our eyeballs and see 21, so 21, and we'd estimate one place further. So if my meniscus is here, I can see that that is just beyond half, right? As in this is the halfway point, and that is just beyond half, so I might say 21.7. or 21.6. And either of those would be reasonable measurements for this water reading in this graduated cylinder. Yes, does that make sense? All right, now here we have, a digital instrument. When we have a digital instrument, it is already estimating that last place for you. So if I was measuring this, I would simply say 16.43 grams. I'm not going to make up something else for the last because there's no way for me to assess that, right? All of that's happening inside the balance. Yes, digital, write down what it says. But what that does mean is that for this balance, right, this is its estimated place, right? Meaning that it is certain through here, and that last space has an estimation. And every digital device that you buy will have on the bottom or on the side or in the instruction manual something about what its level of accuracy is, like plus or minus 0.01 grams or plus or minus 0.05 grams, right? In that's the variation or the uncertainty in its measurements. All right, now how to read significant figures, right? So here we're just going to go through these and count the number of sig figs. Some of these are very easy, right? Like for example, this one, that has 6 significant figures. That one should be easy, right? Scientific notation is always easy because whatever is out front is significant. So this is going to be 3 significant figures. Now, this one is simple because there's only one digit, so it can only be 1. Now, zeros are where things get confusing, right? Here, we have a 0 after a digit, no decimals involved, so this is still only 1 sig fig, in that 0 is a placeholder to give us a reference on size, right? Because 1 is not the same as 10, right? So we can't say 1 and 1. Here, this 0 serves to give us a reference to size. Same thing here. This is still only 1 significant figure. But again, the zeros give us reference to size because these also aren't the same, right? Those zeros tell us how big this 1 significant figure is, right? Here, though, we have zeros that come after a digit and after a decimal, right? In which case, then they all count, right? So here we have 5 significant figures. Here we have that one. So only 1 significant figure. If we think about decimals, a number can't be significant until we reach like a number, right? Something that was measured, right? So here, these are placeholders, right? Because again, 0.1 is not the same as 0.01. And again, this is to give us a reference to the size, right? So this is still 1 significant figure, 1 significant figure. Here though, these zeros come after a digit, after a decimal, so we have 3 significant figures. And we can think about it like, why would we put those zeros after if we didn't need them, right? Because the zeros out front are the placeholders, right? These are the ones that give us a reference to size. These ones after give us a measure of precision, right? Like, how certain are we that it's 1, right? It's 1 out to that many decimal places, right? Here, right? These would count because they're after digits and decimals, and we've got this extra one here, right? So 4 significant figures, and here's same principle, right? We've got some placeholders. We reach our measurement, significant, 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 right? So we've got 5 significant figures. It will get easier as you practice and see more numbers, right? Now, that's important, right? Partly because 1, right, we are writing down measurements and we need to know how many digits to write. Based on the quality of our measurement, right, that's going to affect how many decimal places or how many digits we keep when we do math. Because obviously the whole point is we need to be able to do math with these numbers, right? So here, let's say that we are doing multiplication and division. What is the rule for multiplication and division? Right, least number of significant figures is what we'll keep, right? In that, the least precise measurement determines the precision in our answer, right? So here we have, we have 2 sig figs. Here we have 1 sig fig. So this lesser quality answer determines how much precision can be in my answer. 1.5 times 2 is 3. I can only have 1 sig fig, so that's it. Now let's think about our units. If I take centimeters times centimeters, what do I get? Right, centimeters squared. So the answer here is 3 centimeters squared. no decimals, nothing extra, because one significant figure is the limit of my precision. Here, I have 6 significant figures and 3 significant figures, which means I'm going to be limited by the 3. If I take 1,000 and I cut it in half, I'm going to get 500. And it says I can have 3 significant figures. So options include I could just do this, or scientific notation is always an option, right? And so that would be the best choice, right? And then grams times nothing gives me grams. So all I did was I took my number of grams and I cut it in half and I got 500. Okay, addition and subtraction is the least number of decimal places, right? Addition and subtraction is the least number of decimal places. Here I have 1, here I have none, which means that my final answer will have no decimal places. So I have 3.5 centimeters, because centimeters plus centimeters is like x plus x, so 3.5 centimeters, but I can only have, I can't have any decimal places, which means I have to round this to 4 centimeters, right? So here we're getting some significant rounding because that's the accuracy of my measurements, right? Here, if I have 1,000, which is 2 decimals, and this one, which is 3 decimals, and I add those together, I get 1,000.5, but I have to have 2 decimal places, so 0 grams. Yes? All right. And then the last chunk of this set is Introduction to Conversion Factors. Make sure you have these memorized. And you'll also memorize your SI prefix table, right? And these are things where you're going to practice them now, and they'll seem hard for just one moment. As you keep practicing, they'll get easier, and we will keep using these through May. Super important. Make sure you understand them. As you start practicing, like I said in the syllabus, right, if you don't understand them, if you're getting the skill builders and the end of chapter questions wrong, come see me ASAP, right? You and I can sit down, talk through them, figure out what's wrong, and get you on the right track pretty quickly, right? But if you wait till the end of the chapter, right, it's going to become a bigger and bigger problem. So think about that. Note derived units, right? That's when we take pieces of information and put them together, right? So instead of just saying 1 inch, we might say 1 inch squared, right? Or 1 gram per centimeter, or 1 gram per centimeter cubed, right? Anytime we take more than one piece of information and put it together, then we are talking about a derived unit, right? Where this is a length, here we have what? Correct, an area. Here we have what? Right, a density, right? Okay. Stay tuned. In the next section, we go over lots of problems and work them through together to try to get us all on the same page. All right, thank you for listening. Be good, and I will see you soon. Bye.